Hello, welcome to another module in this massive open online course. So, we are looking at the applications of linear algebra specifically in the context of LDS, that is linear dynamical systems, and autonomous linear dynamic systems. Let us now look at what happens when one inserts, right, the eigenvalue decomposition, or one essentially gets the eigenvalue decomposition into the picture of the particular matrix, right. So, let us look at autonomous linear dynamical systems and what implications does the eigenvalue decomposition have in the context of LDS. Okay. So, we are looking at LDS, and what we are interested in looking at is what are the implications of EVD, that is the eigenvalue decomposition for LDS. As you well know, these are linear dynamical systems, right. So, this is a and this is the EVD, which you must well be familiar by now. This is the eigenvalue decomposition. Now, let us look at what happens. Now, we remember the fundamental equation for EVD is you have your V bar dot equals H V bar. V bar dot is nothing but dV bar dot by dt, and the solution of this is interestingly given as, this is an autonomous linear dynamical system, input is 0, solution is given as V bar t equals e raised to the power of, you might remember this is e raised to the power of t times h into V bar 0, where this is a very interesting quantity. This is what we have termed as the matrix exponential. This is what is termed as a matrix exponential. Now, let us look at what happens, how can you derive further insights into this solution of the autonomous linear dynamical system using the eigenvalue decomposition. Alright. So, let us start with the eigenvalue decomposition of this matrix H. Okay. So, we have H equals U lambda U inverse. This is, remember, this is the eigenvalue, this is the eigenvalue decomposition, and remember it satisfies the property H U equal to lambda U, where U is the matrix of eigenvectors Now, let us specifically look at, and lambda, remember this is the diagonal matrix of eigenvalues, lambda equals, you can write this as lambda 1, lambda 2, so on up to lambda m, if this is an m cross m matrix. So, these is the rest of the entries are, of course, these are zeros. So, this is basically a diagonal matrix of eigenvalues, and what happens here is that now we will form. So, this is the M cross M matrix of, so this is, let us say, M cross M, U is the M cross M matrix of eigenvectors. Let us say U equals U1 bar, U2 bar, Um bar, these are the M eigenvectors. Okay. Now, what we are going to do, now observe an interesting problem. Let us see what is going to happen to H raised to the power of n, right. So, because H is a square matrix, remember I can compute, always compute H raised to the power of m, that is multiply H with itself n times. Okay. So, let us look at H raised to the power of m. This simply means that the matrix H is multiplied with itself n times. Now, substitute the EVD. So, we substitute the EVD. This becomes U lambda U inverse U lambda U inverse, so on and so forth, U lambda U inverse. Now, you look at this U inverse into U, this becomes identity and so on and so forth. So, you will have U inverse, you will have U over here and so on and so forth, and U lambda U inverse and so on and so forth. So, naturally all these U inverse U, this will become identity, all you will be left inside are these lambdas. So, this will be U, so this will be U times lambda times lambda times U inverse. So, it will be this n times, and this is ultimately equal to U lambda to the power of n U inverse. So, this is an interesting expansion. So, what you will see is H raised to the power of n in terms of the eigenvalue decomposition has a very simple expression. It is simply the eigenvalue decomposition is U lambda U inverse, H raised to the power of n is U lambda raised to the power of n U inverse. So, you simply take the matrix of diagonal matrix of eigenvalues lambda, raise it to the power of n, which means that each eigenvalue is raised to the power of n, lambda 1 to the power of n, lambda to the power of n, so on, and multiplied by U, post multiplied by U inverse. So, and now you can see this is nothing but lambda raised to the power of n will simply be lambda raised to the power lambda 1 raised to the power of n, lambda 2 raised to the power of n, lambda m raised to the power of n, and so on, and this will be U inverse, right. So, this is basically your lambda raised to the power of n. So, you are simply taking each eigenvalue computing its nth power, all right. Now, let us now look at, therefore, what happens to the matrix exponential. Now, let us ask the question, what happens to the matrix exponential. Remember them, recall the matrix exponential e raised to the power of t h, that is equal to I plus t h plus t square h square by 2 factorial plus t cube h cube plus 3 factorial, which is equal to I plus t times u lambda u inverse plus t square h square by 2 factorial, that is t square by 2 factorial u lambda square u inverse plus t cube by 3 factorial into h cube, which is nothing but u lambda to the power of 3 u inverse plus so on, which now of course the identity matrix also I can write as u times u inverse. So, net what is this going to be? This is going to be u times this is going to be I plus t lambda plus t square by 2 factorial lambda square plus t cube by 3 factorial lambda cube plus so on times u inverse. And now if you look at this, you will notice something very interesting. This is nothing but e raised to the power of lambda t. What we mean by that, this is simply, if you look at this is simply u, remember, e raised to the power of lambda 1 t, e raised to the power of lambda 2 t, so on and so forth, e raised to the power of lambda m t times u inverse, and this is nothing but e raised to the power of, I can call it as t lambda, where lambda is the diagonal matrix of eigenvalues. So, therefore, you can write e raised to the t h is u e raised to the t lambda times u inverse. So, this is a very interesting property, because this tells you what is the matrix exponential in terms of the scalar exponentials, right, a scalar exponential. So, all this is you take the eigenvector matrix u inverse and take each eigenvalue, raise it to the power of e raised to the power. So, you have e raised to the power of t lambda 1, e raised to the power of t lambda 2, e raised. So, these are scalar matrix, this is not, these are the scalar exponentials, right. So, you can see these are essentially, this is your e raised to the power of lambda 1 t, e raised to the power of lambda 2 t, e raised to the power of lambda m t. So, each of these is a scalar exponential, right. So, these are basically the scalar exponentials. So, it gives us a convenient, because we can easily evaluate the scalar exponentials, we cannot easily readily evaluate a matrix exponential, but the scalar exponentials we can easily evaluate. So, all you have to do is you take the scalar exponentials of the eigenvalues, construct the diagonal matrix, pre-multiplied by u, post multiplied by u inverse, that gives us the matrix exponential. So, this is essentially a very convenient way to evaluate the matrix exponential. Okay. So, this gives us a much easier rather than go through the much easier mechanism, or you can say algorithm to evaluate matrix exponential using the scalar exponentials using the scalar exponentials of the eigenvalues, right. So, this is a very interesting expression. Now, let us look at this further. So, we have already seen h u equal to lambda times u times lambda, that is essentially what we have, where u is the matrix of eigenvectors, right. In fact, to be more specific, I can call this right eigenvectors, which is what we usually mean. So, this is what we mean by default, right. So, and therefore, this gives me h of u equal to u lambda, this you bring u to the right. So, this gives h equal to u lambda u inverse. Now, there is also a notion in which you can define the left eigenvector. So, if you take u inverse on the left, you will have u inverse h equals lambda u inverse. Now, if this u inverse, you can think of this as comprising of the rows w 1 bar transpose, w 2 bar transpose, w m bar transpose, then what you can see clearly here is each w I bar transpose into h equal to lambda I w I bar transpose. So, these rows of u inverse are the left eigenvectors. Okay. So, you can, so these are, although we will not deal with these frequently, these are the left eigenvectors. These are rows of the matrix u inverse. So, by default we will always consider the right eigenvectors, but it is also useful to remember this notion of left eigenvectors. That is, if you take the matrix of right eigenvectors u, take the inverse u inverse, rows of that will be the left eigenvectors, eigenvalues are the same. Okay. Now, so we have u inverse, just to be clear, you have u inverse will be w 1 bar transpose, w 2 bar transpose, w m bar transpose, which as you can see will also be an m cross m matrix, and these are essentially the left eigenvectors. Now, let us look at the solution of the LDS, right. Therefore, solution of the LDS becomes solution of the LDS or specifically solution of autonomous LDS. For simplicity, we will only deal with autonomous LDS where the inputs are 0. So, the solution of the autonomous LDS is, remember, v bar t is e raised to the power of t h v bar 0, right, and this is, now we can write this as u e raised to the power of t lambda, where lambda is the diagonal matrix of eigenvalues, u inverse times v bar 0, which now if I expand this, so I can write v bar t equals u, which is the matrix of left eigenvectors or right eigenvectors, but we will simply call this as eigenvectors. Wherever we need, we will explicitly mention only the left eigenvector. So, e raised to lambda 1 t, e raised to lambda 2 t, so on, e raised to lambda m t times, now we have u inverse which is essentially your W1 bar t multiplied by, of course, whole thing is multiplied by V bar 0. So, this will be W2 bar t multiplied by V bar 0. So on, you will have W m bar t multiplied by V bar 0, which now essentially you can easily see this can be written as k equal to 1 to m uk bar e raised to the power of lambda k t w bar k transpose V bar 0. So, you can think of these, each of these as a mode, right. You can think of each of these as essentially you have m modes, right. So, you can think of this. So, this is your V bar t, right, and so you can think of this as m modes, right. So, the kth mode is essentially, so this is essentially your kth mode. This is the projection of V bar 0 along W k bar transpose, remember, which is the left eigenvector, and this grows, this is, you can think of this as the growth factor, this is growing as this growth, this is the growth e raised to the power of lambda k t, and this is the final direction, this is along. So, essentially the way you can think of this is essentially you are taking V bar 0. So, kth mode, it has 3 components. First, take the projection along the left eigenvector, that is your the right left eigenvector, that is W k bar 0, then grow it as e raised to, grow it exponentially with the rate lambda k, which is the kth eigenvalue, that is e raised to lambda k t, and finally which is the direction along which the kth mode is pointing, that is u bar k. Okay. So, therefore, this is basically project along W bar k. So, you can think of this as 3 steps, essentially project the trajectory, project along W bar k transpose, grow as e raised to lambda k t, and finally this is whole thing is along u bar k, alright. So, this is basically your, it essentially is your an interesting way to think about your autonomous linear. So, you project it along, so the projection along the kth left eigenvector grows at the rate lambda k and pointing along u bar k, which is the kth right eigenvector, which we will also call simply as the eigenvector to avoid any confusion. Eigenvector always implies by default right eigenvector. If it is a left eigenvector, we will specifically mention it. So, let me also write that down, eigenvector implies right eigenvector by default. Okay. So, do not get confused. Now, it is essentially interesting to see when, now one can ask the question, when is the system stable, right, when does this V bar t, when does this go to 0 as t tends to infinity. So, you can see V bar t tends to 0 as t tends to infinity if magnitude lambda k is less than 1, right. If magnitude lambda k, if magnitude lambda k is, so or lambda k is v bar k tends to 0, if, or you can say this is bounded essentially, this is essentially bounded, right. This is bounded if magnitude lambda k less than 1 implies this is stable if magnitude lambda k, or e raised to, or you can say this is stable if e raised to, therefore e raised to lambda k t tends to 0 as t tends to infinity. This implies e raised to lambda k t less than 1, this implies lambda k less than 0. So, if e raised to lambda k t, if this is essentially, if this quantity is essentially less than 1, or essentially the lambda k is, if the eigenvalue is less than 0, then we can say the system is stable. Okay. So, these are the interesting interpretations that one can derive from the eigenvalue decomposition, right. So, interesting things one can derive. So, essentially what you can see is that the eigenvalue decomposition gives you a very convenient mechanism to compute the matrix exponential in terms of the scalar exponentials of the eigenvalues. So, you simply take the scalar exponentials of the eigenvalues and pre-multiply by u, post multiply by u inverse, that gives you the matrix exponential, and one can use that in the solution of the autonomous LDS, and the solution can be described very simply. You take the projection along the left eigenvector of the initial starting point, that is v bar 0, grow it as e raised to lambda, go the kth mode as e raised to lambda k t, and finally this points along the direction u bar k. That is essentially a very insightful and intuitive form of expressing the matrix exponential. All right. So, that I think presents a very interesting application, and remember all this relies heavily on various principles of linear algebra, of course matrices, matrix multiplication, the eigenvalue decomposition, projections and so on. So, again that shows how matrices can be used to efficiently compute the solutions of several complex systems, and in this particular example the autonomous linear dynamical system, which as we have shown has very interesting applications even in the context of circuits. Remember we built an example with a circuit, a simple circuit with two capacitors and 2 resistors, and showed how that can be modeled as a linear dynamical system. All right. So, essentially this basically can be used as a technique to solve complex systems. All right. So, let us stop here and let us continue this discussion in the subsequent modules. Thank you very much.